is r times theta evaluated from 0 to pi, right? And so we can calculate that, and our answer is 2 pi. All right, so last two-dimensional, and so now we're going to. So I think we're going to sketch, right? We get these handouts, but I think it's a really good practice to draw circles, right? And put in your axes and think about how you can, identify this plane, right? So we've basically taken a chunk out of that circle. You're looking all the way into the origin. And now we're going to allow this vector to not be in the plane of the screen, but to be coming out towards us a little bit. Okay? And it still has a zenith angle theta, still has a length of r, but we can drop a projection of that vector into the xy plane. And when we do that, we can identify the azimuth angle relative to the x-axis. Okay. And in doing so, we can take that projection or that vertical here, and let me make sure that I've got the right color here. So we can take that projection down and we can just move it over here onto the z axis. So it's the same length. It literally is, I literally fixed it. So it's the same length. Okay. And then we can draw the other side of the triangles in green, and those are the same length. And so we can equate those triangles. And I'm going to just paste it up here. And I did literally just paste it. So it looks not quite the same as when it's in that circle, but it is exactly what was in that circle. And so if I look at that triangle and recognize that in this view, it's sort of back, it's folded back into the board. So which one of those angles is the right angle? A 90-degree angle. So we know that it's not this one, right? We know that this angle is the theta angle, right? So it's got to be either the one on the right or the one on the left. Which one do you think it is?
Top left.
Top left, top left. Does everyone get that? So it's this angle, right? I'll draw it. That's the right angle. And that's really important to identify. Okay, because then you can do your SOHCAHTOA, which you remember from whenever you took trig. Now, we talked about how you know the relationships of the sides and the opposites and angles, but you don't call it SOHCAHTOA. What do you call it?
I don't know what to call it in English. So.
I know, but what would you call it when you were in school?
Fine.
Just like cosine, so just opposite over adjacent,
Yeah.
or okay. So I mean, it's an important thing to think about. In English, SOHCAHTOA is the sine of the angle is the opposite over the hypotenuse. the cosine is the adjacent over the hypotenuse, and the tangent is the opposite over the adjacent, so katoa. But if you are not a native English speaker, that is not your mnemonic. So you should have one that works for you, right? Or you have to memorize the one. But I think it's just important as we recognize that what can be so familiar to half the people in the class is so not familiar to the other people in the class. So always remember that when you're like doing your work or teaching or whatever. Do you have one? What's yours? So katoa, right? Okay. All right, so we're gonna use that relationship. That is a really bad right angle sign. Sorry about that. Okay. All right, so what that means is that we can identify the hypotenuse and we can identify the opposite and the adjacent sides relative to angle theta. Okay. And I color code, I try to color code things, and if you're colorblind, I apologize, but I do try to pay attention to the font color and the line color to kind of help you identify things. Okay. So, and we also know that the hypotenuse h is equal to the radius, right? So we know one thing. All right, so that means that the sine of theta is opposite over hypotenuse, which is radius, right? And that means that the length of that opposite, if I solve for O, that is equal to r sine theta. And so I just pasted it in up here. Okay, that's the length of that. It's not quite r, it's scaled by the sine. All right, so now we can do the cosine relationship, and that's going to be the adjacent over the hypotenuse, or a over r. And that tells us the length of the projection of our projection of this vector onto the z-axis, right? So I can write that as r cosine theta. Erase what I just did there so you can see it. Okay. So we'll do that. Okay, so if we're projecting our vector onto the z-axis, we can now say that the length of that projection is r cosine theta. And what we're going to do is try to project it onto the other axis. So now we're going to look in the other planes. Okay, so if we project the vector back onto the xy plane, and we look at where it projects onto the x-axis, that's the red line. Okay. And so that's going to give us that length projecting onto the y-axis. So the length of the red line are equal along the y-axis, and we can see where it's going to intersect the x-axis. And then we can draw the other parts of that in yellow. Draw the projections the other way, projecting onto the y and the length of the x projection. So the yellow is the length of the x projection, the red is the length of the y projection. Okay. So now I'm going to grab one of those triangles and put it up here. Which angle is phi? Is it phi or phi? Huh?
I do both.
Why?
I don't know. I don't have a
Do
reason.
you know when you do it? Do you know when you say phi, when you say phi?
Probably of relevancy thing, whoever said it last in my head.
Right? So here's what Kurt Mobley says. You say pi or p. We say pi, so it's phi. You don't want to pee on pi. And now you never forget. Okay, which angle is phi? That'll make a mistake, I'll call it phi. Which angle is phi, is the azimuth angle in that one? The top, right? So it's this one. Okay, which is the right angle? How many people say left? Anyone say right? When you think about the projection? Okay. So we'll do a better job. That's the right angle. So that allows us to identify the opposite side, which is which one? The opposite side of the angle phi is red, okay? And what's the hypotenuse? Green, and so that makes yellow adjacent. And so now we can go through and solve, and so now what we know is the length of the green line, because I color coded it, is no longer R because it's been shortened, right? It's not R because it's not down in the XY plane. It's R sine theta. And so the length of the hypotenuse on that triangle is R sine theta. Shorter than R. And so the sine, of course, is the opposite over the hypotenuse, but the hypotenuse is R sine theta. And the opposite side is the red one, the red lines. And the sine, or the cosine of phi, is the adjacent over the hypotenuse, which is the yellow side, the length of the yellow side over R sine theta. So then I can project that the projection of my vector in the XY plane onto the y-axis, so its length along the y-axis is going to be the length of the red line, which is my opposite. So I have to use the sine phi function. And so it's going to be this one. Is going to give me this. And so it's R sine theta sine phi is that projection. And if we want the length of the projection in the XY plane onto the x-axis over here, it's going to be the length of the y line, the yellow line, and that is the cosine relationship. So that's the way you can project in spherical coordinates, okay? It's just geometry. It's just figuring out which triangle you're working with. And so what I recommend that you do is to do this yourself and come up with a nice little cheat sheet for yourself and keep it. Because I did this when I took this class 100 years ago, because no one did it for me. And I couldn't do it in my head fast enough to keep up. And I still have my original sketch from 1987. Okay. It's just, it can be really helpful. When you just have it all the time, then it just becomes easy. It just flows for you. Just make it easy. All right. So why do we need to do this? Well, we need to do this because we're trying to think about solid angles. And we've been talking about solid angles when we talk about the Collin scattering function. We're talking about solid angles when we're talking about radiance. And so we are doing this projection to try to figure out what that, in the same way that we look at the arc length of the circle, we want to know the projected surface area of a tiny solid angle. So there's our little area, and that little area is defined by some small increment of theta, and it's defined by some small increment of phi, projected onto the sphere. And so I'm going to remind us that the length over there is R sine theta, because when I move that little surface area out into space, I know that the length that I'm trying to get here is R d theta. It's the length of R times that little increment of d theta. But when I'm looking at the other side, this length over here, that is going to be R sine theta. And you can figure that out if you take both slides and put them next to each other. You'll be able to figure that out. I'm going to let you do that. You can convince yourself what the lengths of those two parts of that little surface area are. So what is that surface area of that little, infinitesimal small surface? Approximately a square, what would it be? Would be what? Yeah, so you can just multiply them. One side by the other, r d theta and r sine theta d phi, right? And so you simplify that and it's r squared sine theta d phi. Sorry to sound a little familiar. But let's make sure we've done it right, because we have to integrate. So we're going to integrate that little infinitesimal portion of surface area for the whole sphere, right? And we know what the surface area of a sphere is, or we should, or you can look it up, or it might sound familiar when we get there, right? So we're going to integrate d phi from 0 to 2 pi. So we're going to go all the way around d phi. And we're going to integrate d theta from 0 to 2 pi. So you can think about this as I've subtended my 0 to pi, right? So I have this semicircle. And this is the axis. So that's my semicircle. And now I'm sweeping with that semicircle. I'm sweeping around in 2 pi. And I've created a sphere. See that? Okay. You always have to check yourself to make sure that you've done the integration limits correctly, right? If I've just gone 0 to pi over 2, then I'm sweeping out just the upper hemisphere. Okay. All right. So when you do that integration, your r squared comes out, and you get a phi that you're evaluating from 0 to 2 pi. And then you have to integrate the sine theta d theta, which is minus cosine. So that's a minus cosine evaluated from 0 to pi. And this is a multiplication sign. Mult, not x. And so what we get is, if I can erase what I've just written there. That we're evaluating phi between 0 and 2 pi, that just gives you a 2 pi. And then we're evaluating the cosine, the minus cosine from pi to 0. So what's the cosine of pi? Minus 1. So that is minus 1 times the negative sign is 1. So it's a minus a negative 1. And then we have minus a negative cosine, so that's going to be plus. And then what's cosine of 0? 1. So we have a negative 1, which is plus, and a negative of a negative 1, which is plus. So that's 2. Excellent, because that gives us 4 pi squared, which is the surface area here. Okay. All right, excellent. Keeping track of your negative signs is the hardest part, and remembering your unit circle. All right, so what that means is that analogous to that arc length, the arc length L over R was equal to d theta in 2 dimensions. We can say that the surface area divided by r squared is equal to the solid angle. But we know what ds is because we just solved for it up here. And so the solid angle is sine theta d phi. And that is the integrand that you use when you're doing scattering function and you're integrating over all solid angles. That's gonna be the solid angle when you're looking at radiances and you're integrating over the light field. That's how you can divide it. That sine theta is there because it's part of the solid angle description. Spend some time with it. It'll become customary. But it's not magic. It's just, it's religious geometry. Okay. All right. Yeah. So you remember that we have different sensors. We have a radiant sensor, which is, we use the term L, and radiance is a function of that azimuth and the zenith angle, and it has units of micromole photons per meter squared per second per steradian, or you can express it in watts. There's a conversion, and we talked about the first day. But it is per solid angle, right? That's where the steradians are coming in. The irradiance, planar irradiance, is related to some integration of the radiance. But remember that you're only concerned, it's only measuring the vertical component of the light, of the radiance that's incident on the sensor. And so that is where the cosine of theta comes in. Because the horizontal part of that vector does not intersect with the plane of the sensor. So we don't measure it. So that's where the cosine comes in. So in order to shorten it, I just did the solid angle as d omega, but remember that that d omega is really sine theta, d theta, d phi. So now what you're seeing is that you have radiance, you're integrating radiance times cosine times sine, d theta, d phi. And so you have to keep track of that when you're integrating. And so for the downward irradiance, we're integrating for all azimuth angles, but just 0 to pi by 2. 0 to pi by 2 in theta. So the units no longer have the steradians. So you have no solid angle dependence because you integrate it over all the things. So no steradians. And then the scalar sensor, the one that looks like a light bulb, which we'll have today for lab, essentially doesn't matter what direction the sun or any light is coming in, because no matter what direction it's coming in, it will intersect that sphere at a 90-degree angle. And the cosine of 90 degrees is 1. So it's like having an infinite number of cosine sensors wrapped around you. Like a little cosine sensor here, a little cosine sensor here, an infinite number of them all the way around. That's how you can do it. And so that, when you're trying to calculate that from radians, you are literally just summing up all the radians and you are not scaling it by the cosine. There's no cosine. But again, this is sine theta, d theta, d phi here. So the sensor you're gonna use today, it's a PAR sensor that is a scale of PAR. And the reason why biologists tend to purchase this sensor is because phytoplankton absorb light this way. They do not do cosine scaling. They're beyond that math. All right, so remembering those, now we're going to do the radiative transfer. This. Back to the favorite stock image. And now you can see the rays of brightness and the shadows caused by the focusing. Let's see what those are now. You can see Snell's cone. You can actually see the texture of the surface in the light field. All right, so what we're going to do is describe how radiance changes along the path of propagation. So I picked one of those rays and I just drew a vector representing the radiance at 1 theta and 1 phi. And so what we want to try to describe is how the radiance changes along that path. And so you should immediately be thinking of Charlotte, because she just talked to us about how radiance is changing as a function of depth and along the path, right? So you should already be thinking about things are going to attenuate, it's going to get smaller. But we don't tend to take a radiance sensor and point it at our light and then measure it down that path, right? We don't move our sensors this way in line with the direction of how that radiance is propagating. That would really be a pain in the neck, right? What we tend to do is take a reading at that angle and then lower our sensor down in depth and take the reading at the same angle, like this. Okay. We tend to put it on a wire and do a bottom depth, right? So the light is not traveling along that vertical path, it's traveling along the yellow path. And you can define that as the theta, the zenith angle, and of course, you can come up with a correction. And guess what? It's a cosine, because everything's cosine, right? So the cosine of that angle is dz over dr. And so we can substitute, we can solve for dr and put it in here. And what we get is that this term, looking at how radiance decays along a path, is going to equal how radiance decays with depth multiplied by the cosine of the angle at which that radiance is propagating. Okay. Just geometry. Is that good? Okay. So you got here on Monday. We let you play around on Monday afternoon, and then we jumped in on Tuesday to talk about IOPs, right? What was the first IOP we talked about? Absorption, yes. And we went in the lab and we measured absorption. So that is not an accident that we talked about absorption first. So one of the first things that I think about is what is happening to radiance as it's propagating through the oceans that it gets absorbed. And so we might show that as like, I had a lot of light and then I ended up with not as much light. Okay. And so the amount of radiance that's absorbed along that path is simply the absorption coefficient times the radiance. But it's a loss term, so it's negative. Because we don't tend to express our absorption coefficients as a negative sign. We express them as positive. So there's a loss of radiance along that path due to absorption equal to the absorption at that depth interval, at that wavelength, multiplied by the radiance at that depth and wavelength. at that angle, 35 angles. All right. Then the second thing we talk about is scattering. And first we're going to talk about scattering out of the path, right? And so that might look something like this. We had a lot of radiance coming in, we ended up with less because we lost it out of the path. And this radiance sensor can measure this amount of radiance, but it's not going to measure that or that because it's not pointing in the right direction. That would end up in some other theta and phi measurement. We haven't lost any energy, we've just lost it from our path at which we're measuring. Whereas absorption, we did lose that energy. That energy is gone. It's gone into photosynthesis, it's gone into heat. We don't get it back. Unless, of course, it was absorbed by chlorophyll and you get it fluoresce in another wavelength. But you don't get it in your measurement. You have a good sensor. All right, and the amount that's lost is simply the scattering coefficient times the radiance. And it's a loss term, so it's negative. And then we save the hard one for next. We save the scattering into the path. So that is going to look something like this. Radiance from some other angle being scattered by a particle into your angle of interest, your theta and phi. And so what do you need to know to figure that out? We need the volume scattering function, because that's going to describe radiance in one direction being scattered in another direction. So the scattering into the path is the volume scattering function expressed as a function of theta and phi, but it's of the theta and phi of radiance coming from another direction. Right? So radiance coming from one direction, which is going to be theta prime, phi prime. Again. Getting scattered into, and this will be some theta phi, scattered into your direction of interest based upon that volume scattering function, right? And you can imagine that the volume scattering function in response to that is peaked in the forward direction and smaller in the back directions. But there will be some portion of the scattering that will go into the theta and phi of your radiance measurements, this one, into this direction. And so you have to account for radiance coming from every single direction times the volume scattering function pair that will send it into your theta and phi of interest. So that's why you have to integrate over for all radiances. So you can have radiances coming in at any direction, and each one of those will have one single pair of scattering that will get it to go into your system. So those of you who got the BSF instrument over there, it's that times the full radiance distribution. And you're just going to get one little piece of radiance out of it that's going to go into your radiance of theta and phi. You're going to do a lot of math to figure out just how much you got out of it. All right, good. Okay, the last one is fluorescence. And I'm not going to write out the equation because it's really brutal, but imagine that phytoplankton absorb radiance and emit fluorescence. Or CDOM absorbs radiance and emits fluorescence into the angle in which you are examining it and into the wavelength in which you are measuring it. So it's a source, some source of radiance at your depth from that was absorbed at lambda prime, some higher energy wavelength, shorter wavelength, and is fluoresced into the wavelength that you are measuring. at your theta and phi. So this could be Raman, this could be CDOM fluorescence, it could be chlorophyll fluorescence, anything that has taken it from one wavelength to the other. And of course, what this means is that as you're measuring your radiance, you've done all these calculations for 440 nanometers. Some of the absorbed radiance, A times L at 440 that you calculated, some of that energy gets moved into your measurements at 676. So it's linked to your processing of your data set in the blue. If you knew how much of that absorption is due to photochromatic, and how much of that photochromatic absorption is due to chlorophyll, and how much ended up the rest. There's a lot of factors, efficiency factors, absorption factors, blah, blah, blah. That's it. Those are the terms. But now we have measured all of those. You have seen the instruments that do that. And so compared to last Tuesday, you are much better equipped to be able to actually think about each of these terms, right? So if I gave you a knowledge survey, you'd be like, well, I measured the absorption. I've measured the volume scattering function. We just talked about solid angles, so I bet I can figure it out. At least sketch a diagram. All right, so there it is. We put it all together. The change in radiance at some azimuth and zenith angle, at some depth and at some wavelength. The gradient in that, or the change in that with depth, multiplied by the cosine to account for that path length difference, is equal to the loss due to absorption, the loss due to scattering, the gain due to scattering from another angle, and the gain due to a source at another wavelength. And you can sketch it like that, right? Loss due to absorption, gain due to scattering, loss due to scattering, gain due to fluorescence. All right. Stand up. Put your arms over your head, take a deep breath.
Bow to you.
Very good breath. Get all that oxygen. Woo, big stretch. Ah. You did some good work. So now let's do single mutation. Okay. But you can't solve that. You can't analytically solve it. So let's do some simplification. So there it is. I've combined the minus A and the minus B terms because A plus B equals C. So that's one simplification. That was very easy. Okay. And I've taken off the source term because I'm going to say that right away when we're done with sources. All right. So if we integrate this, if we integrate each one of these terms over all solid angles, it's going to get us somewhere very cool. So let's integrate this term. Well, I don't remember the last time you guys each had integral calculus, or if you had it. So let's try and just pull out something that looks familiar. I have a radiance and I have a cosine. If I have the product of radiance times the cosine and I'm integrating it over a solid angle, what radiometric quantity is that close to? ED. So even if you don't know how to integrate, you can remember that a radiance times a cosine that's integrated is going to get you ED. Okay. Except we're measuring it over 4 pi. So here's the problem. You have a bunch of light coming down, right? And And then you have a bunch of light coming up. Okay, so this is EU. And this is ED. But when I integrate from 0 to pi, and I'm getting a positive number, that's positive down. When I integrate from here to here, it's going in the opposite direction, so it's a negative number. So it's not quite ED. It's actually the net downward. It's ED minus ED. And we write that as E with a vector, or sometimes E with a hat. Depends on the textbook, make sure you check. But it's the net downward irradiance. And physicists love this because this gives you a sense of how much net energy is making down into the ocean and not making it back up. That energy can go into heat. Okay, so that's a really important term when you're thinking about modeling heat. And so what we're left with when we do this integration is we still have the derivative. We're just looking at the depth gradient of this net irradiance. But Charlotte just gave us a lecture on depth gradients. What is the depth gradient of this? We're looking at the depth gradient of E. We have a term that's close to that. K, did you say K?
Yes.
Yeah, so we're getting close to K. We're not quite there yet, but we're close to K. So when you see that, just start thinking like, oh, we're getting towards another term that I think I know. Okay. All right, let's do the next term. Now we're going to integrate C times L over all of the angles. So now we're looking at the integral of L, but no cosine. And C is not dependent upon angles, so pull that out. What's the integral of L without a cosine? Scalar, right? It's the scalar. Awesome. It's exactly the scalar. Woo! Right. Ready for the last term? Last term's the bear. Okay. So we're going to integrate that over all solid angles. Is there a cosine in there? Well, these are sine theta, d theta, d phi. No cosines in those solid angles. So no cosine dependent, no cosine times radiance. So when you integrate it over angles, what radiometric quantity? Just integrated radiance without the cosine. You integrate it all over all angles. You just did it. It's still scalar. And when you integrate volume scattering function over all angles, that's if you integrate the phase function, which is normalized. But if it's the actual value of scattering at every angle, and you integrate it, it's B. Right? You just integrate it under the volume scattering function curve, and that's scattering. Right? So now we have B times the scalar. Well, this is just shaping up. Right? Because now when we put those integrals together, we get this. We get that the change in the net downward irradiance with depth is equal to the loss term of attenuation times the scalar. Because I had minus A, and I had minus B, and it equals minus C. And then I have the addition, is how much we gain into the path, and it's just B times the scalar. So crazy that, because I can combine these two terms, can't I? We can factor it, right? It's E naught 0 or E0 times minus C plus B. What is minus C plus B? know that. A plus B plus C. It's mentioned. So by integrating over all solid angles, we find a relationship that the gradient, the depth gradient in net downward irradiance is equal to the absorption coefficient times the scalar irradiance. So we just did our first approximation of the radiant transfer equation that relates radiometric measurements to IOPs. So you just made yourself an absorption meter from a radiometer. What? Four radiometers? Oh, 4 radiometers, yeah, like a really nice radiometer system, right? Because you need to measure the downward, you need to measure the upward, you need to measure the scalar, right? So let's divide both sides by minus E minus the net downward, and we're going to solve for absorption. The reason is that this term over here is not quite K. Not quite K. But if we divide both sides by the net downward, then we get this term, which is K. And the net downward irradiance divided by the scalar. So that is a ratio of something that has directionality to something that doesn't, which is an average cosine term. It's one of the other ones that Charlotte talked about. So it turns out that the absorption coefficient is equal to the attenuation of the net downward irradiance times the average cosine of the angularity of the light. And so you can calculate absorption from these measurements. And that is very cool. And so people have done it. And we did it on an experiment a couple of years ago. And Meg showed this example on day 2, 3, 2. From this paper, from Kostakis. So these are 12 different stations in the inland waters around Florida, not inland, in the intercoastal waterway. Measuring absorption with the ICAM, not the great instrument, AC9, ACS, the SciCam integrated cavity, and the dotted lines are Gershon. And so David Peake came out with his radiometer system. And while all the instruments were sitting at 1.5 meters, measuring absorption, he measured profiles of light, of irradiance and scalar irradiance, and calculated A. And I'm just saying, not so bad, right? But these measurements are on very different spatial scales. The AC meter is measuring like this little bit, and he's measuring over big volumes of light coming in. So you wouldn't expect them to be exactly on top of each other. You would expect them to be close. So we didn't have it for every station, but I would say that that's not bad. So it's another tool you can get. Okay. Yeah.
Can you remind me of the assumptions we made for meaning, just no sources?
So we took out fluorescence.
Okay.
We took out fluorescence. So you're assuming some homogeneity, right? And if you're doing it, so what you're assuming is the depth over which you're doing the calculations, you have some homogeneity, right? If you have really sharp gradients in A and B, it's going to get very complicated, and the values won't be as. So not a bad way to get close to them. All right, what time is it? I passed. You want to keep going? All right. All right, this is less math and more just like quickly. Let's look at this. Okay, so here's our equation. There's something called successive order scattering. You'll see it in some of the optics theoretical papers. It's a way of taking the radiant transfer equation and separating the radiance term, saying, I'm gonna separate the, in an additive sense, I'm gonna say, I'm gonna look at radiance that never got scattered. And I'm gonna look at radiance that got scattered once, radiance that got scattered twice, so, and so you can separate it, and so you can separate the radiance term into these different amounts that radiance has been scattered, okay? So that's successive order scattering. You can solve some cool solutions using that approach. Or you can do something called the single scattering approximation that says, I'm only going to consider the radiance that is unscattered or singly scattered. So I'm going to ignore all the other higher order scattering terms. Okay? And that becomes pretty powerful if you're only looking at those events, but it places some constraints on where you can make this approximation. You can't make this down at the bottom of the photosome because you had multiple scattering by the time. So you're limiting yourself to the surface. Yeah, exactly. So then we make this other assumption. We say, well, if that's the case, if you're going to make that approximation, then I'm going to make a further approximation. I'm going to say that if you have a radiance coming down and it hits a particle, that the volume scattering function are usually pretty forward peaked. And so a lot of the light is getting scattered downward. If it's scattered downward, I'm not going to see it coming back at me. So I can ignore it. It's like it never even got scattered. It just continues on its path. So light coming down, it's a particle, gets scattered in the forward direction. That was your single scattering. Can't get it back up because you're not going to allow it to scatter a second time because you're not going to count it in this approximation. So it might as well not scatter. So forward scattering is like no scattering at all. So that means that anywhere in the radiative transfer equation where you see a B, you can replace it with BB because you're going to ignore BF. And anywhere in the equation where you have beam attenuation, you're going to replace that with A plus BB because you ignore forward scattering. Okay. So you still have to solve these terms, and the math is tricky, but Kurt does it in like 100 pages of his book. So you can follow that. But what it means is that the upward light field that you see coming out of the ocean is the result of downward light that got scattered in the backward direction once. And so it's proportional to backscattering, the amount of light that's coming out of the ocean. And it also is that the light that's coming down, that's getting scattered back up, has been attenuated. But we've already made an assumption about attenuation. We said it's A plus BB instead of C. So what that tells you is that if you're looking at an apparent property of upward light over downward light, it's the ratio of this. And so Emmanuel talked about reflections, and it can be LU over ED or EU over V. Any one of the upward terms over the downward terms is going to be proportional to the backscattering, which is what got it back up in the upward direction, divided by those properties that attenuate. So how many people have ever looked at reflectance as being a function of V back over A or V back over A plus V back, right? This is it. These are the assumptions that you made. So my question to you is, when can you use this relationship? More importantly, where in the water pump? At the surface, right? So don't be doing profiles of R and inverting it for B back over A plus B back, because it does not hold once you get into a multiple scattering machine. Okay, you'll see some papers in the literature where that was done and not done correctly. But that is the type of approximation that gets you, again, relating a radiometric measurements used to calculate an apparent optical property and relating it to IOPs. So now you've done it twice. Congratulations. That's how much. I'm tired. Are you tired?
No.
What'd you say?
So everybody have lunch ready at 1:15, be at the lab ready to go